My name is Adam Bowman. The publication I decided to choose for my final project is a website that details the workings and mathematics of a simple ideal inverted RC op-amp known as an integrator circuit. And you can see the citation for the web page down here. So this is an integrator circuit, a simple one. And I'm not really going to make too many changes to it for this project. Actually, none at all, really. So an integrator circuit does pretty much exactly what it sounds like. You give it a voltage, an input voltage, and what happens is there is a relationship between the voltage that you put in here versus the voltage that you get out here, depending on the value of these components and the frequency of the signal, the shape of the signal, things like this. Let's see, there are some limitations. For instance, mostly having to do with frequency. If you have, let's see, you're given a sinusoidal wave and the frequency is too small, there are some physical properties of a capacitor that will cause it to act as an open loop, and you will not have a functioning amplifier. So this is the main mathematical model that relates the output voltage along with the values of all of the individual components. And you can see that the larger that your resistance and your capacitance are, the lower your voltage is going to be that you get out. And what's also interesting is you can see that all these values have variable relationships in here, except for this op amp over here. What's interesting about it is that its presence in this equation is actually presented by the integral, the operator itself. So this is not a variable; it's actually a mathematical operator in this setup, due to the way that the capacitor stores charge and then phase shifts it, specifically if you're putting in a sinusoidal wave. So this is the Simulink model that I used. You can see the picture from the last slide over here, and you can also see how it mirrors the image here. It's going to look a little bit different from the regular Simulink models that we've been using, because this right here is actually represented in a slightly different program within MATLAB called SimScape, which is for physical modeling, and that's what these boxes are here. This is, let's see, basically a sine function that you would have in Simulink, but to use it in here, you're actually going to have to put it through an algorithm that gives it some physical properties, some physical modeling properties. And so then once you do that, you can pass it through and it behaves basically just like a regular physical circuit. And then you're going to have to take that signal and you're going to have to transfer it back to a Simulink signal, something that it can read. Okay, so one other thing I wanted to show is this right here. This might look pretty familiar to what we've seen in class because it is very familiar. It's very similar. Basically, this entire circuit here is built off of the idea, the relationship between voltage, capacitance, and charge on a capacitor. And you can see that eventually, if you work your way through these equations, you'll be dealing with VC, V out over here. And since, here, let me pull up the Simulink model. Wrong one. Okay, so you can see here that what really makes this work, when you follow the equations through here, is the fact that I in, right here, the current that you're getting in, because of the properties of this op amp, are actually going to be the same as the current across this this node here that contains the capacitor. And because of that relationship, you can get this direct relationship here between V out and V in and the values of each components. You can see that, as I said before, you're getting the negative integral. So let's see if I run this, and here is my, let's see, my original output voltage. And then I can, let's go over here to where I'm getting, excuse me, input voltage. Now let me check my output voltage. And you can see that they've been shifted. It's, of course, the integral of sine is actually negative cosine, but the negative of that right here would just be cosine, so it worked properly. Pretty cool. And the amplitude depends on the R and the C that I give it. And the frequency is the same as the input frequency. You notice frequency is not in these equations. So what's interesting about this too is that when you go and you change R and C, despite what you might think, it actually has the exact same result on the circuit. So let's say I go over here to, let's see, scope over here, yep, and let's say I take my capacitor and change it from microfarads to regular farads. Let's see what that does differently to my output over here. Look at that, still 10 volts, but to the negative third power. And I can mess around with that value a little bit. And when I do, you can see, let's see, I'll go back to milli so you can see. Run it again, and okay, see, and then do it one more time. Go in the other direction. Go to microfarads. All right, see that? So yeah, pretty cool. And well, actually, the very cool thing about it is now let me put it back to the original value, which was at let's see, I had it at microfarads, and now let me change. Okay, give it this. Should go back to, oh, that's the original. So let me pull this one up. The output voltage here. Let me change the resistor from 1 ohm to 1 k ohm. Look at that, pretty cool, right? So it does exactly the same thing as, and you can see that in the equation, but basically what that means is that if you're going to pick out components when you're designing your amplifier, it basically means that whichever is easier for you to manipulate, it doesn't matter, just pick that one because they both have the exact same result. Let's see. That's pretty much it. Those are the results that I've checked out so far. Any changes that I do further will end up in my final report, and I hope everybody enjoyed learning about integrated circuits, or integrator circuits. Sorry, it's something completely different. Thank you.